Hey everybody! The purpose of this video is to get us some solutions to the switchback quiz that we had posted. That is wobbly. Let's stop that right now. There we go. I want to make sure that the reason that switchbacks are placed places like in roads and trails is mathematically as well as intuitively obvious to you. So that's, again, the purpose of the quiz. So I'm looking at the quiz down here. I've got a picture of a road that is switchback. We also looked at a few of them in class together, and I'm sure if you have ever traveled in Oregon exclusively or extensively, you've been on a few of them. So the idea really is you've got an elevation, say here, we'll call it E1, and you have to go uphill to an elevation, say it's E2. I mean, whatever that is. And I say it's uphill. So there's going to be a hill. It's like a nice green hill. And there's a hill between them. Let's just make it go kind of like that. And it's steep. And you could very easily go straight from point E1 to E2. Okay, so clearly, if you do that, you will have gone a certain run and you've gone a certain rise. Now again, you can do this the right or the wrong way. This would be the run coming across here, and this would be the rise coming up here. And if you look over here, this would be the hypotenuse, but we oftentimes substitute the hypotenuse for the run. We've talked about doing that the wrong way. Now, in the picture, what I've shown and what you would see if this were a three-dimensional chalkboard is you'd see instead of going directly from E1 to E2, you would come from E1 out to some other point, maybe about here, and then switch back to E2. So the idea is you break up that by coming out here and then going back there. And again, wish it was more three-dimensional, but I think we can reason through this. So the idea is to now analyze that mathematically. So the first question, which was if road A has a larger average grade than road B, which would be easier to walk or bike or drive up? And I realize that's a loaded question because we haven't talked about what easier means. What does it mean to be easier? When I run stairs on campus, I take them 2 at a time. Some people say that if they try to take stairs 2 at a time, it wears them out quicker. I say taking stairs 1 at a time wears me out quicker. So that's why I define easier. Define easier in this case as less energy expended at the hardest point. Okay, that's number 1. And number 2 is assume that a higher grade equals more energy expenditure. So what's kind of silly about this is I've given you the answer. Since energy expenditure corresponds to, or higher energy expenditure corresponds to higher grade, obviously I've just told you that the road B must be easier because road A has a higher grade. So I've given you the answer. I'm not even sure why I don't know. Gave you the answer. So there you go. Now here's the mathematical part. The next 3 questions. Boom, boom, boom. The rise, the run, and the rise over the run, the grade. So the analyze the ride, analyze the run, and analyze the grade. So this guy here I was calling the fall line route. So here's the fall line route. Okay, if we were to roll from E2 back to E1, that's the same as going from E1 to E2. So compare that to the switchback route. Okay, so first thing I ask you to do is to compare the rises. So here's the rise. This is the rise. You start at this point, and you rise to that point. Okay, fair enough. Now again, this is where a three-dimensional manifestation would be great. But if you start at this point, you come out to here, you've now risen, if I can do this in the camera, you've now risen about this much. And then we got to go up to here. We've now picked up the rest of it. So you see the rises are the same because you get to the same vertical point, right? You start at E1, you get to E2. It doesn't matter if you go directly that way. If you come this way, it also doesn't matter if you go back and forth, back and forth, back and forth, and then come across horizontally. It doesn't matter, technically speaking, if you ignore the route you take. If you go up above E2 and drop back in, you've risen the same amount. You've started at this elevation and gone to this elevation. Fair enough. So that's an equal sign. How about the run of the switchback route versus the run of the fall line route? Okay, so again, this technically you can consider to be the run, although this could be the run too. I think on that footnote, I want to check, I think that the footnote says, yeah, feel free to use the hypotenuse, because it doesn't matter. The same logic applies either way. So in which do you cover more horizontal distance? We cover the same vertical distance in rise. So do you cover more horizontal distance going that way, or coming out here and then heading back in there? Now some of you might argue, well yeah, but what if you only come out a little tiny bit and then go back in? Well, let me offer you another view of this to kind of make sense. Imagine you were a bird looking down at these two roots, okay? So imagine you were a bird, here's a bird's eye view. A bird's eye view, okay? And you got E1 and you got E2. They are going to be connected directly by the fall line route. Here's what the switchback route would look like, basically. If you're looking down on the road's under you now, okay? What's longer, that piece or these two pieces added together? And you might argue to yourself that, well, it's pretty obvious. But what if the switchback were tiny, like this? Or even tinier than that, like this? Or even tinier than that, like this? Which is longer? Well, I can guarantee you mathematically the pink switchbacks are always longer because of something called the triangle inequality. In any triangle whatsoever, any two sides added together must be larger than the third side. Now, that's a cool idea, but here's why it always has to be true. Assume they're not, right? Assume that there exists a triangle where two sides are not together bigger than the other side. That means they're either equal or less than. Let's go with the less than case because the same argument will apply to the equals case. So that means you've got a triangle somewhere, and I'll put it over here, okay? And then you've got that length, sum total length lessened, and these two pieces here are going to be less than that. Well, there's no way they can come together, right? They're too short. This plus this is now less than that. That means they're never going to make a triangle. So in other words, as soon as you try to create a triangle off of this length, as soon as you bring these sides up, in order to make them connect, you have to make them longer, which means those two sides have to be bigger than that. So guaranteed, the switchback route is going to be longer in run than the fall line route. So the next symbol is going to be greater than. All right. And last but not least, for the average grade, the rise and the run and the rise of the run of the fall line. So I want to look at this one fractionally. You've got rise, oh, we're going switchback first, right? Rise, switchback over run, switchback. Rise, fall line over run, fall line. Roof. It's kind of a fun word. Okay, let's get a color here. Blue red. Okay, so we know automatically that the rises are the same. They're the same thing. So if that's 1, that's 1. If that's 2, that's 2. If that's 3, that's 3. And I don't care what we're measuring these things in. You can make up any unit you want. So these guys are equal. I'm going to put a blue box around that. They are equal in size. So if you're thinking about a balance scale, that's the same weight on both sides of the balance scale. How about the runs? Well, we just decided that the run of the switchback is larger than the run of the fall line. So whatever this is going to be smaller. And it doesn't matter how much smaller. We're looking for a generalization here. So if this were 1 and this were 1, this might be 5, and this might be 4, or 5 and 3, or something like that. So now you have to realize something. And these are fractions, right? In these fractions, the numerators are the same. The denominator of this one is bigger than the denominator of that one. So let's think about what that means with a few examples. Suppose the fractions were 1/3 versus 1/2, or 1/4 versus 1/2, or 1/10 versus 1/8, or any number of possible examples. On which side is the larger fraction? On which side is the smaller fraction? What's bigger, 1/3 or 1/2? Well, 1/2 is definitely bigger. 1/4 or 1/2? Definitely 1/2. 1/8 or 1/10? Well, 1/8. Because since you've got the numerator the same, the larger denominator means that that fractional chunk is being broke into more pieces for the same size chunk. Well, if it's more pieces for the same size chunk, that means the pieces themselves have to be smaller. Which means these pieces on the left side have to be smaller than the pieces on the right side. Which means this guy right here, the switchbacks grade has to be less than the fall lines grade. Which is the whole point, remember? If you lessen the grade, you lessen the energy expenditure, whether it's in a car, whether you're walking, whether it's on a bike. So the last inequality sign there is a less than sign. So it goes equal, greater, less than. It was kind of fun how that worked out like that. Cool. Now you know the mathematics of switchbacks. The next time you're hiking up one or biking up or down one, you can truly appreciate it. See you on the Mackenzie.